Hello everyone, welcome to chapter 13, all about trigonometric identities. Yes, we're not moving too far away from trigonometry just yet, and we're introducing something called identities. So this will be a fairly short chapter, just a couple weeks, especially short compared to our last chapter, which spanned, maybe a couple months there. And we'll be reusing some of our knowledge about sine, cosine, tangent, all of those other trig functions. So let's go ahead and determine or define, I guess, what is a trigonometric identity. And we're just going to call that trig identity to shorten that going forward. So a trig identity, this is something you'll want to add to your notes. This is going to be an equation that involves trig functions that is true for all values for which that equation is defined. So that last phrase is kind of important. We're saying that some trig identity is an equation that works always, with exceptions. There will be some exceptions that when we state, okay, here's an equation, we're going to call this an identity, we will actually state, oh, but except for this particular value. So you'll see that bullet point there. Sometimes we will specify those certain values that are excluded from the identity or represent restrictions on the identity. Remember back to our domain restrictions when we were working with rational equations. Because oftentimes those values would make our equation or make our identity undefined, and we don't want that. So for example, we'll see restrictions. It could be something like theta can't be equal to 90 degrees, or what we'll see more often is the sine of theta can't be equal to, for example, 1, or the cosine of theta can't be equal to whatever. So we'll look at those going forward. Let's see, so an identity has to be proven rigorously using known definitions, mathematical properties, existing identities, etc. So we're going to be looking at later on a process called verifying identities, and we'll look at that a little bit today as well. So any identity does have to be proven for all values of theta. We'll sort of look at what that really means. Doesn't mean we have to go through 0 through 360 degrees and show that it works for all of those degrees. That's not exactly what we mean. However, if we want to disprove an identity, suppose we're checking, is this thing an identity? We can show that it is not by showing just one counterexample, just one value of theta that doesn't satisfy the equation or makes the equation not true. So we'll keep those in mind. In fact, why don't we look at a quick example of trying to prove an identity? So let's take a look at this first. Cosine of theta plus sine of theta equals 1. We want to answer, is that an identity? Well, let's see. Maybe let's take a value of theta just to test for now. So let's plug this in. Cosine of pi over 2 plus sine of pi over 2. We want to know, is that equal to 1? So we might need to go back to our unit circle and figure out, okay, what exactly is cosine of pi over 2 again? Remember, if we were to translate that from radians into degrees, we'd be looking at 90 degrees. So we're looking at our unit circle perhaps. Let's pretend that's a nice circle. Right up here is our pi over 2, or our 90 degrees. So of course the coordinates there are 0 and 1. The cosine value corresponds, of course, to the x coordinate, so that would be 0. The sine value, right at that same angle, corresponds to the y value, so we'd be looking at 1. Ah, interesting. So in this case, for this one value of theta, this equation does work. That's a true statement. Now, what if we were to try, though, a different angle? Let's look at that now at 3 pi over 2. So now 3 pi over 2, that's still on our unit circle, and this time it's down here. The coordinates are going to end up being 0 and -1. That also is 270 degrees. So if we were to plug this into our equation, cosine of 3 pi over 2 plus sine of 3 pi over 2, is that equal to 1? Well, the cosine value is still 0. The sine value is now -1. So we can see we have come across a counter example. 0 plus -1 is not equal to 1. So this proves that this equation, cosine of theta plus sine of theta equals 1, that is not an identity, because we are able to determine a counter example. Okay, so in this particular lesson, we're going to go through some of the most, common, most basic trig identities. So my recommendation for you watching this video and ideally taking notes is to make yourself a little table that looks kind of like what we see on the screen right here. We're going to be talking about 3 types of identities. Quotient identities, there's going to be 2 of those. Reciprocal identities, there will be 6. And Pythagorean identities, which there will actually be 3 of. There should be another bullet point down there. So maybe I'll add that right here. We should have a third little space there for one more identity at the end. Now, I would recommend giving yourself some space to write out the equation for each identity and note the restriction that corresponds to that identity. Each of the ones we're going to talk about have restrictions, so we will have a restriction to put for all of these. We're not necessarily going to prove all of these. We will talk about where they come from, however. Why don't we dive in, and you might want to pause so that you can copy this table down into your notes. But once you've got that ready to go, we'll talk first about quotient identities. So quotient identities, these are the first 2 identities. The equation, we'll start over here with our tangent of theta. The equation is tangent of theta is equal to sine of theta over cosine of theta. Our restriction is that cosine of theta cannot be equal to 0. We can see that if that was equal to 0, all of a sudden our equation would say sine of theta over 0, and that would cause this equation to become undefined. We don't want that. Now the other identity over here is cotangent of theta is equal to cosine of theta over sine of theta. So sine of theta, therefore our restriction is sine of theta cannot be equal to 0. So same reasoning, we don't want the equation to become undefined. So I just want to talk briefly for these 2 kind of where this comes from. So we're going to sort of recall again back to our unit circle, where if we had a, let's say we had some point on our unit circle forming an angle in standard position. I guess I'll draw my axes too. Okay, so of course any point on the unit circle has an x and a y coordinate. We talked about just before that the x coordinate is our cosine of theta, whereas the y coordinate is our sine of theta. We also, in the last chapter, talked about, well, if we're looking at an angle on the unit circle, how do we determine the tangent value? Well, the tangent value of our angle is always going to be equal to the y coordinate over the x coordinate. So now we're saying, well, we don't care necessarily about the coordinates on the unit circle. We care, though, about figuring out our cosine and our sine and using that in our equation. So that's just the same thing. Let's see, I wrote that reverse, I just realized. Sine over cosine, my goodness. Let's get that straight here. Sine of theta over cosine of theta. Okay. So we are saying for this particular equation that, okay, cosine of theta can't be equal to 0. Well, when would cosine of theta actually be equal to 0? Again, let's think about the unit circle. When cosine of theta is equal to 0, that means theta would have to be, like we talked about in the last example, 90 degrees, or we could talk about radians, pi over 2 radians, and also 270 degrees, or 3 pi over 2. So technically saying theta can't be 90 degrees or 270 degrees or pi over 2 or 3 pi over 2, that could also be considered our domain restriction. However, that is just a little bit messier than simply writing out, don't let cosine of theta be equal to 0. So that is why you'll see this more often, just saying that this function can't be equal to 0. This whole denominator can't be 0, or the whole thing becomes undefined. Okay, let's look then at our next identities, which are our reciprocal identities. The reciprocal identities will mostly look familiar. So there are 6 of them. You may want to pause and kind of add all of these into your table or into your notes otherwise. Notice, of course, after each equation, we have the restriction. So the restriction for our first one is that cosecant of theta can't be equal to 0. So these are fairly straightforward. I don't think we need to spend a ton of time on talking about where these come from. When we introduced the 3 reciprocal trig functions, cosecant, secant, and cotangent, well, we defined them as reciprocal identities. We talked about cosecant being equal to the, the hypotenuse over the opposite, whereas, of course, sine is equal to the opposite over the hypotenuse. Now we're saying, well, if we're still talking about cosecant, it's the reciprocal of sine. By definition, the reciprocal of anything is 1 over that same thing. So that's where these functions are kind of coming from. We're saying sine of theta, it's the reciprocal of cosecant, so it's equal to 1 over cosecant. Cosine is equal to 1 over secant. Tangent, 1 over cotangent. And then we have all of our reciprocal functions as identities as well. Cosecant is equal to 1 over sine, secant 1 over cosine, cotangent 1 over tangent. Okay, those are the reciprocal identities. Now the next set is our Pythagorean identities. These we will spend just a little bit more time on. They're kind of fun. They're where we will often start when we are simplifying or when we are verifying identities. These we come back to very frequently. So the first, let's look at those. There we are. Reciprocal identities. Oh, let's see. I'm just going to skip over that. There we go. So our Pythagorean identities, here we go. These are the 3 of them. Notice no restrictions in this case. Cosine squared of theta plus sine squared of theta is equal to 1. That's our first Pythagorean identity. No restriction. Works for all values of theta. The next, tangent squared of theta plus 1 is equal to secant squared of theta. So notice how I'm reading this function with the little squared piece here. Tangent squared of theta. Our next identity, or our last identity really, that we're going to cover in this chapter is cotangent squared plus 1 is equal to cosecant squared. So I often drop sort of saying like of theta when I'm looking at identities, just to make it a little bit easier to talk about. So we could say from the beginning cosine squared plus sine squared is equal to 1, or cosine squared of theta plus sine squared of theta is equal to 1. we want to remember to always include theta when we're writing out our identities. We don't want to drop it, even if we're like not saying it out loud. Okay, so if you've got all these written down, then excellent. We're going to move on to talking about where they come from. If you want to pause and get them all copied down into your notes, excellent. Let's start with that first one. Cosine squared plus sine squared is equal to 1. So again, we're going to back up, look at the unit circle. I'm going to draw out just a little set of axes, and let's say this point is actually on the unit circle. So let's draw out our reference triangle. Let's pretend that actually gets to our origin there. So being on the unit circle, of course, the hypotenuse of this right triangle is equal to 1. Our our opposite side will be y, or sine of our angle theta. And our adjacent, or x, will be equal to the cosine of theta. So we've got a right triangle here, and we have all of the sides defined in a couple of different ways. Let's also recall our Pythagorean theorem. These are Pythagorean identities, so they're based in that Pythagorean theorem that tells us when looking at a right triangle, the two legs squared, remember the legs are the two sides attached to the right angle. So those two legs squared, we often say a squared and b squared, added together will equal our hypotenuse squared. So we'll call that c squared, as we usually do. So let's substitute, though, our known information here. So first of all, maybe we could say that like a is x. So we could say like x squared, that's just one of the legs, meaning, okay, y would have to therefore be b. So we'll have x squared plus y squared is equal to, okay, 1 squared, 1 is our hypotenuse, 1 squared is just 1. Now if we substitute, though, our values for theta into x and y, what will we get? We can write that perhaps as cosine, I wrote parentheses O, let's see, cosine of theta squared. Okay, sine is equal to y, so sine of theta squared, that's equal to 1. This is our identity. We've written it maybe a little bit differently. Rather than writing cosine in parentheses and then squared on the outside, we just want to move that exponent right by our cosine. Cosine squared of theta is how we'll write that instead. Sine squared of theta, that is equal to 1. So that is where our first Pythagorean identity comes from. Literally just looking at our reference triangle from some angle on the unit circle and plugging in our known information into the Pythagorean theorem. So let's look then at the other two. The other two, we are going to actually start with this first Pythagorean identity and kind of manipulate the equation a little bit. So let's do that. The next one is our tangent squared of theta plus 1 is equal to secant squared of theta. Or if, like I said, I was going to drop saying of theta all over the place, so just tangent squared plus 1 is equal to secant squared. So like I said, we want to start with really our original Pythagorean identity. Cosine squared plus sine squared is equal to 1. So I want to actually manipulate this a little bit. I'm going to multiply this entire equation by something. And that something I'm going to choose to be 1 over cosine squared. I'm going to just multiply the entire equation by that. So let's pull that down. Cosine squared plus sine squared equals 1. So we are multiplying both sides because we're multiplying the entire equation by this 1 over cosine squared. So we're going to need to distribute to all three terms that are involved in our equation. So what does that make? Let's see. We're going to end up with a cosine squared over a cosine squared. Then we have a sine squared over a cosine squared. Okay, and then 1 times 1 over cosine squared, that's just going to be 1 over cosine squared. Okay, so that's where we're at now. This is equivalent to what we started with. We've just now multiplied it by cosine squared of theta. Okay, so let's see, our cosine squared over cosine squared, this first term here, that's just equal to 1. So we have 1 for that first term. What about this second one? Sine squared over cosine squared. Well, I'm going to ask that we remember one of our original identities that we already talked about. One of the quotient identities, in fact, that told us that tangent is equal to sine over cosine. Well, it turns out we can square this entire equation and it is still true. Tangent squared of theta is equal to sine squared of theta over cosine squared of theta. And that's exactly what we have back over in our original equation. We can take this sine squared over cosine squared and say, oh, that's actually the same thing as tangent squared. Okay, what about this 1 over cosine squared? Well, I think we can use one of our reciprocal identities here. So in fact, let's write that out. We know that 1 over cosine squared is equal to secant squared, or I could have written that the other way, secant squared, or secant is equal to 1 over cosine. It's saying squared when it's not there. We can square this though and say, okay, 1 over cosine squared is actually equal to secant squared. So that's what we'll do. We'll take this 1 over cosine squared and say, oh, that's actually secant squared. So what we have is our identity from up above. Maybe our terms, we just want to rearrange in the slightest. Tangent squared plus 1 is equal to secant squared. So that's again where our second identity comes from. Now, very, very similar idea for our last one. Let's look at that. Cotangent squared plus 1 is equal to cosecant squared. Let's take that and multiply it by something. We're again going to start with our cosine squared plus sine squared is equal to 1. That's again sort of the original Pythagorean identity. So let's take this and multiply it this time by 1 over sine squared. Let's see what happens here. So again, we're multiplying the entire equation, which means we need to distribute 1 over sine squared across all three of these terms. So we'll get cosine squared over sine squared. I think hopefully we're seeing a way to maybe rewrite that first expression. Let's keep going for now though. Sine squared over sine squared. Okay, hopefully we're also identifying a way to simplify that. And lastly, 1 over sine squared. 1 times 1 over sine squared, we just end up with 1 over sine squared. Okay, let's simplify. Cosine squared over sine squared, that looks like our other quotient identity. So it's not equal to tangent this time, but it is equal to cotangent. And it's equal to cotangent squared. Again, notice our squareds here. Okay, next up, sine squared over sine squared. That just simplifies simply down to 1. And then lastly, 1 over sine squared. This is one of our other reciprocal identities. And the reciprocal of sine is cosecant. So we'll say this is equal to cosecant squared. And voila, that is the identity. Cotangent squared plus 1 is equal to cosecant squared. Okay, those are all of our identities. Let me just say right now, for this particular class, we are not asking you to memorize these. You will be wanting to be familiar with them and have them perhaps handy. So having a nice organized table will be really handy while you're going through your homework. If we were in school physically, I did this last year. I passed out like a little cheat sheet of just a list of the identities with their restrictions, and encouraged students to use that while they went through their homework, while they did quizzes and tests, etc. Now, memorizing these trig identities is something that you'll want to kind of just be aware of. It's coming in, say, pre-calculus or future math classes. So while we're not asking you to do it this year, it is something that you want to be familiar with, and hopefully just know that that's on the horizon for future math classes. Now, let's real quick also try to use these trig identities. That's kind of the point. Like, why are we even looking at these random equations? Let's look at a few example problems. So this is one type of problem we'll see where we are asked to find some function, in this case tangent of theta, if secant of theta is equal to -2. So we're asked to find some function, we're given some other function. We are also given a particular quadrant that we're saying theta should be in. So this quadrant, let's see, between 180 and 270, theta lies. Let's look at our quadrants again. We know this is 0, 90 degrees, 180, and 270, and of course back to 360 over there. So if we are looking at any theta values between 180 and 270, that means we're down here in quadrant 3. So we'll kind of come back to that idea in a bit. Let's review sort of our general technique, our general problem-solving process for something like this. We're starting with, start with an identity, one of those that we included in our table, that actually includes or uses both the given trig function, so in this case we're looking for one that includes or involves tangent, and the function we're trying to solve for. And that would be, I guess I kind of got that mixed up. We are looking for some identity that uses secant and tangent. So let's look at our list. We've got all those Pythagorean identities. We've got our quotient and our reciprocals. I think the only one that I can really identify that uses both secant and tangent is one of the Pythagorean identities. So the one that starts with tangent squared plus 1 is equal to secant squared. Okay, so that's where we want to start. Our next sort of step is to then substitute, this should have an extra little t in there, the known value into this identity. So we know that secant of theta is supposed to be equal to -2. So secant of theta, well, we have in our identity secant squared of theta. Remember, another way that we could write that is secant of theta squared. That might help us see what we need to do a little bit more clearly. We're going to just plug in -2 for secant, and we need to square that to get secant squared. So -2 squared, of course, is going to give us 4. So that makes our equation overall tangent squared plus 1 is equal to 4. Okay, now we need to solve. We're solving again for tangent of theta. So let's see. Looks like maybe I can subtract 1 from both sides. So we'll end up with tangent squared is equal to 3. Okay. And if I'm just solving for tangent, and what I have right now is tangent squared, then I guess I need to take the square root of both sides. I'm just going to say we're going up this way. Square root of tangent squared is equal to the square root of 3. Okay, so that means our tangent of theta is going to be equal to the square root of 3. Now the last step in our problem solving kind of technique here is to determine the correct sign of our solution based on where we are for the sort of definition of theta here. We've already determined that if we're looking at values of theta that are between 180 and 270 degrees, then we'll be in quadrant 3. So if that's the case, what is tangent? Is tangent positive or negative in that particular quadrant? Well, x and y coordinates in quadrant 3, x chord and y chord, are they positive or are they negative? They are both negative. So the x and the y coordinates are negative here. In that case, remember that tangent, that's equal to, well, we said that's equal to sine over cosine. We also know it's equal to y over x. So in theory, that's going to be some negative number over some other negative number. Maybe it helps to write like parentheses around there. And a negative over a negative, of course, results in a positive. That alone tells us that our answer should be a positive square root of 3, not a negative square root of 3 and not a plus or minus square root of 3, just positive square root of 3. Okay, let's do maybe just a couple more kind of quick examples. So maybe you want to give this one a shot on your own. If so, go ahead and pause and unpause once you've got your answer. Okay, so we have sine of theta, that's what we want to find, and we're given that cosine of theta is equal to -1/2. So the trig identity that I'm going to start with is going to be cosine squared plus sine squared is equal to 1. Again, I want to pick an identity that involves both of these given functions that I'm working with, and ideally not other ones. Like I don't want there to be a tangent when I don't have any information about tangent and I'm not solving for it. So this is what we'll start with. So we'll plug in our known value, that known value being -1/2, and we have to square that. Okay, so let's write what else we have. So this is what we're solving, and again, we're solving for sine. So when we square -1/2, it's going to end up being a positive 1/4. Remember, we square 1, we also square 2, square the numerator, square the denominator. Okay, and I'll just write the rest of our equation out here. Okay, so in order to solve for sine square, or solve for sine, that is, I need to, I guess, subtract 1/4 from both sides. So we'll end up with a sine squared is equal to 3/4. Okay, and again, we're going to need to take the square root of both sides. Maybe we'll do that over here. Square root of sine squared is equal to the square root of 3/4. So that tells me sine is equal to, okay, the square root of 3/4. I think we can simplify that a little. Remember, when we have the square root of a fraction, we can take the square root of the numerator and the square root of the denominator. And fortunately for us, the square root of that denominator is a nice whole number. So we'll rewrite this as square root of 3/2. Now we just have to figure out, is it supposed to be positive? Should it be negative? What's the deal here? We want to go back to our definition, our given restriction on theta. So this time it's between 90 degrees and 180 degrees. Again, let's just sketch out our quadrants. 90 degrees and 180 degrees, we're looking at quadrant 2. In quadrant 2, what are our, what's the sign, I guess, of our x and our y coordinates? X coordinates over here are negative, but y coordinates are positive. So remember, what is sine? Is sine an x coordinate or a y coordinate? On our unit circle, sine is always the y coordinate. So that tells me that my answer in this case should be a positive value. So we would write as our answer that sine of theta is equal to the square root of 3 over 2. Okay, one more quick example. Okay, this time cosecant of theta is what we're finding. We're given cotangent of theta is equal to negative 3/5. All right, and of course we're given that theta should be between 270 and 360 degrees. So as a quick reminder, that's going to be our quadrant 4, okay, where of course x values are positive and y values are negative. Okay, so let's start with figuring out which identity we should be using. Take a moment to look at your list. Maybe pause the video for a second. It's again going to be one of our Pythagorean identities. This one, cotangent squared plus 1 is equal to cosecant squared. Okay, so our known info is cotangent, so we'll plug in negative 3/5 squared plus 1 is equal to cosecant squared. So we're really doing the same process as we did in the last two examples. Let's square negative 3/5. So we're going to end up with 9/25 plus 1 is equal to cosecant squared. Okay, in this case, why don't we go ahead and say, well, 1, let's put that into 25ths. So 1 is the same thing as 25/25. Okay, so we can actually add these fractions together now, and we would get 34/25. That's equal to cosecant squared. Okay, so now we just need to take the square root of both sides. We'll do that up here. Square root of 34/25, that's going to be equal to the square root of cosecant squared. Okay, so of course on the right-hand side, we're just going to end up with our cosecant. But on the left, again, I'm going to take the square root of the numerator and the square root of the denominator. And same as before, we can simplify that denominator. So we'll get the square root of 34 over 5 is equal to our cosecant of theta. Okay, now we just have to think about, is this supposed to be a positive or is it supposed to be a negative? So let's go back to our quadrant. Here in quadrant 4, again, we usually use Roman numerals when we talk about our quadrants. You don't have to, I guess. So our y values are sine, our x values are cosine, but what about our cosecant? Where are our cosecant values? Well, remember that cosecant is the reciprocal of sine. So if our y values, which are our sine values, are negative, there we go, then so is the reciprocal of that, like 1 over sine. Remember, this is our reciprocal identity. Cosecant is also going to be negative if sine is negative in this particular quadrant. So that means I just need to tack on a negative to my answer. Let's make that a little nicer. There's my nice little negative. So our answer in this case is the negative square root of 34 over 5 is equal to our cosecant of theta. Okay, so that's an introduction to our trig identities and ways in which we can use them. Thank you for watching.